This is number 25 from section 10.2, and it's the navigation problem. It's a pretty good problem. An airplane flying in the direction of 20 degrees east of north at 325 miles per hour in still air encounters a 40 mile per hour tailwind acting in the direction of 40 degrees west of north. The airplane maintains its compass heading, but because of the wind requires a new ground speed and direction. What are they? So they use vectors a lot in navigation. And sometimes the techniques change, but as I recall, this is what they do. So if we say, first of all, the plane is flying in still air 20 degrees east of north, so it's usually north, south, west, and east. So if we're going 20 degrees east of north, that means that we're moving just like that, 20 degrees east of north. And this would be the vector, and I drew it in green, and that represents the 325 mile per hour vector, and this is its direction. Remember, it has both magnitude and direction. And our reference angle, in order to break it up into vertical and horizontal components, because when we add vectors, that's the way we do it, it's a lot easier. So we'll use this triangle here. This is 90 degrees altogether, so 20 from 90 is 70. So this is the reference angle or reference triangle. And I can use triangular trigonometry to break this up into its two components. I know that the sine of 70 degrees equals the opposite over the hypotenuse, so the sine of 70 degrees equals y over the 325. And if I multiply by 325, this is my vertical component, and it goes in right over here. 325 sine of 70. And I know the cosine of 70 is equal to the adjacent over the hypotenuse, so the cosine of 70 equals x over 325. If I multiply by 325, x equals 325 cosine of 70 degrees, and that's going to be my horizontal component of my plane flying in still air. Make sure you change your calculator to degrees, because we're going to be doing this in degrees. And then the wind is going 40 miles per hour, and it's going to go 40 degrees west of north. So this is north, and if I go 40 degrees west of north, I just move over 40 degrees west of north in the west direction. And again, 40 from 90 is 50, so 50 degrees will be the angle of my reference triangle, so I can break this wind component into both vertical and horizontal components. So again, we do the same thing. The sine of 50 equals y over 40. Happens to be the same, 40 miles per hour and 40 degrees. Okay? Y over 40, so y equals 40 sine of 50 degrees. So that's the vertical component of my wind speed. And the horizontal component, the adjacent side, so the cosine of 50 degrees equals x over 40. And then I multiply by 40, and I get x equals 40 cosine of 50 degrees. Now, since this is going in the negative direction, I put a negative there. All right? So it's going to be negative x, or it's going in the negative direction. We could say that negative x equals that. So x equals negative, if you want to think of it like that. Either way, this is the horizontal component. Negative 40 degrees. Negative 40, times the cosine of 50 degrees. So these are my horizontal and vertical components of my wind, and the horizontal and vertical components of the plane in still air. You can see that. And if this is a little more complicated, you always can zoom in on this. All right, so we're just going to add these. Now what they do, they have these big charts, and they actually would draw these vectors and measure these angles with a compass very carefully, and they would draw them to scale. So 325, it's going to be more than 12 times, well, 7 times. It should be about the 7 times the length of this, but they would scale it out. So they would have this vector drawn to scale, and then they would take this and they would add tail to head, so they would put the other one over here. That would be the wind velocity, all scaled, and they're using compasses to get the angles exact. And then they would connect tail to head, and then they would get the resultant vector, and that would actually have the magnitude that we're looking for and the angle we're looking for, and it would also trace the exact path that the plane will fly. So that's by using compasses and rulers and measuring these things very carefully. They get a real accurate vector that describes their motion, and that's their direction and their magnitude. Okay, we don't have to do that. We just have to add the components together and get the resultant vector, which is the u plus v. Should have been my u in green because that's the air and the velocity in still air. Okay. And we got this resultant vector, and I just put it all in red. Okay. So when we add these, you can just put these in your calculator. And the first one will be the 325. Now I actually wrote down the values so you can get an idea in pencil. So these are actually the values. I calculated each of these separately. And they should kind of add up, but we can, it's a good way to check it anyway. So we'll say 325. 25 cosine of 70 degrees plus, well actually it's going to be negative, right? Because we're going to, this is a minus, so minus 40 cosine of 50 degrees. All right, we can all see that okay. Looks a little bit dark on my screen. I hope it works out on your screen. And you press enter and you get 85.445. Now that's going to be the horizontal component of my resultant vector. So what I'm going to do is I'm going to, yeah, I just see that there. So I'm just going to store that. So I'll go store alpha A. Enter. Okay. And then so that's going to go in A. And then I'll do the vertical component, so it's going to be 325 sine 70 plus now 40 sine 50, and I get my 36.042, and that's going to be the vertical component of my vector, two vectors added up, and I'll store that alpha B. Okay, so we got those stored. Now we want the magnitude of both vectors added up together. And again, like I said, if you did this, with all your instruments, you would get this. This would be the wind vector here. Would be over here. Then you'd add those up, and then you could just measure that. But we can find the vector by just taking the magnitude of these two vectors, so that's just going to be the square root. Remember, the magnitude would be the square root of a squared plus b squared, or the square root of the horizontal component squared plus the vertical component squared. Now we already have these, so I can just do it like this. This is going to be a squared b squared, so we can just get our calculator out again, and we can go square root, and we could put alpha a squared plus alpha b squared and we get 346.735, and that's your new actual speed. That's your true speed. Okay, that's your new ground speed. That's how you're moving relative to the grounds. Okay, because in the still air you're moving one way, but the wind's moving you another way, so your actual ground speed, if you look at the plane from the ground, that's what's happening. Okay, now we also want to find the angle, so this is my resultant vector u plus v, and we know that the vertical component is 336.42, and this is the horizontal component. We want to find our actual angle, so we know that the tangent of theta will be the opposite over the adjacent. So my angle will be the angle whose tangent is the opposite over the adjacent. We've already got that. That's going to be B over A, because we stored that. So we just take the arctangent. Clear some of this up here. I'll take arctangent, so second tan, and then alpha B divided by alpha A, parentheses, enter, and I get 75.734 degrees. And I can say 90 minus, oh, it's clear. Well, I could just take the difference. I should have done that. Okay, So I'll say 90 minus second answer, and I get 14.26. And the reason why I did that, because this is the angle, and this angle is going to be east of north, I should say. Well, this angle here is going to be north of east, because here's east and here's north. So this angle would be 75 degrees north of east, but we usually do it relative to north, so if we subtract, this angle would be 14.266 degrees east of north. So we usually do everything relative to north or south. Okay? And that's how you get your direction. Hope that makes sense.